Here we have Chapter 7a, Introduction to T-Tests. I recommend you watch the review before you come in here. It might be helpful to you coming off of where we've been. So the one sample t-test, the problem that we're solving with this test is solving the problem of unknown spread. Here's an example. Dr. Russ taught a cognitive psychology course, and she's interested in whether students take more time with news articles after completing the course than people in general. She gathered data from her 15 students and found they spent an average of 180 seconds on a news article after clicking a link. Is this significant? She knew that people in general spent 148 seconds reading a news article after arriving there from an internal link. The data are from a good source. You can see the source of these data here, but no standard deviation is given. How can we do a statistical test with no standard deviation? So here's that question. How can we conduct a statistical test without knowing spread? So here's the problem. She knows that people in general spend 148 seconds reading a news article after arriving there from an internal link. The data are from a good source, but no standard deviation is given. So there's our 148. But how do we know spread? How do we know spread? How do we know spread? How can we determine the cutoff point if we don't know what the spread is? So how can we estimate spread based on our sample? That's what we're going to do in the one sample t-test. Here is the theoretical foundation. Imagine our mad scientist who spent months and years drawing an infinite number of samples from a population that had a known mu and sigma. For each sample, he calculated and plotted the mean and standard deviation. What did he learn? He learned that the standard deviation was typically just a little smaller than the standard deviation for the actual population. So if we estimate the standard deviation based on these samples, it's going to be a little bit narrower. And then he learned what the formula is for estimating variance from the sample. So we wind up with this t distribution. And first, just looking at the picture, you can see that the t distribution is, in this image, has these really fat tails relative to the normal distribution. And so what the t distribution is the hypothetical scores defining the comparison distribution in t-tests, step 2. And in some ways it's similar. So first off, like the z distribution, the t distribution is represented by a curved line that's symmetrical. It's similar to the normal distribution line. It's sort of bell-shaped. And it also represents a hypothetical distribution of an infinite numbers of samples of a particular sign drawn from the population with the means plotted on a histogram. But there are some differences. Unlike the z distribution, the heaviness of the tails differs based on the size of the sample. So the heavier the tails are. Let me just get an eraser here and erase that and just show you what this looks like. So if we erase this and we imagine that we have a cutoff point of 1.65, here's our cutoff point, and this would mean that our reject region would be all of this. But look at how many more scores there are in this distribution compared to the normal distribution. So here in this normal distribution, we have these, right? But we have all of this in our t distribution tail. So we're going to have a lot more score. We're going to have a much different reject region if we do a test like this. And so what we have to do to find out what this distribution is like is we have to estimate the standard deviation using information we get from the individuals in our sample. So here's another image of these distributions and some rules about it. The z distribution is in blue, and it's the normal distribution shape we've been working with. a t-distribution differs based on the sample size. And so larger sample sizes, more than 30, have slightly fatter tails. Look at the t-distribution in red in the chart. And you can see the tails are a little fatter, meaning the cutoff points have to be a little bit higher in order to get 5%. So it won't be that different from the z-distribution cutoff points. But smaller sample sizes have much fatter tails, so the cutoff point is going to be a lot more extreme. And so in order to get only 5% of the values in this green distribution, we're going to have a cutoff point a lot farther away from the mean. Why the different cutoff point? Remember, it's related to the percent of the tail of that's in the tail of the distribution. And in the one in green, we can see that there are just a lot more values in the tail, so the cutoff point has to be further to accommodate 5% or 1% of the values. So in a t-test, here's our mad scientist's formula. We estimate variance of the comparison distribution from the sample. We know the variance of the sample provides a good but biased estimate for the variance of the population, meaning that it's biased in favor of a smaller standard deviation, so we have to divide by a bigger denominator. So we know that again from our mad scientist. The bias is that we have these variances that are just a little smaller than was actually in the population, and so we adjust it. Instead of calculating variance as SS divided by N, like we have done, like we have been doing in the z-test, or what we're doing, we're calculating a standard deviation raw, is we're going to use SS divided by N minus 1. And N minus 1 we call the degrees of freedom. I think I have that written here. And N minus 1 is called degrees of freedom, and it's always, at least in these initial t-tests, going to be N minus 1. So here we have our problem. And we're going to find out how we can find spread for the sample if we know that our sum of squares is 30,000, working with a nice round number. And so the way to figure this out is to first calculate our variance. And in this case, we can't calculate our variance directly. We have to estimate our variance based on the degrees of freedom. So I'm just going to write this out, estimated variance, and I abbreviate this with a lowercase e var, is sum of squares not divided by n, but divided by degrees of freedom, equals 30,000 divided by our degrees of freedom, 15 minus 1 is 14. And if we run that calculation, we get 2,142.86. The next thing we do is just our normal calculation for varm, which is just, in this case, E var divided by n, which is this 2142.86 divided by 15, and this is just to take into account our sample size, which equals 142.857. You won't get these exactly in your calculator. I'm using Excel, so we'll always have that problem of rounding that happens in when I use just certain of the digits. And next we're calculating the standard deviation, the estimated standard deviation for the distribution of means. And we're going to just write this as this kind of italicized S for the distribution of means. And that equals the square root of varm, which equals the square root of 142.857, which equals 11.9523. So let's just take a look at how this might work out in an actual problem. So let's imagine that you read an article stating that students spend an average of 16 hours per week outside of class on coursework, and you think music majors would have a lot more hours practicing and all that. So the research hypothesis, music majors will spend more coursework hours outside of class than students in general. Parse the problem, students who major in music compared with students in general. We're measuring study hours. You'll remember that I am going to change over to referring to population 2 as population 0 because it represents the null hypothesis. The tails, we saw the word more, so it's a one-tailed high. And we have our research hypothesis, which we could also state as mu1 is greater than mu. I'll write the 0 here. And we have the null hypothesis where we just add the word not or we put the equal sign. So here's our problem again, and you can see that we're given data for 5 music majors, and we're asked to test this hypothesis with alpha 0.05. So first off, we're describing the comparison distribution in terms of center, shape, and spread. And we know that for center, we always, grab my pen here, we're going to get mu out of the problem. And it says these music majors in general spend 16 hours per week. Our shape is just normal. And our spread is calculated as the standard deviation, but estimating it back based on the degrees of freedom. So I've gone ahead and actually calculated the mean for this group. We find that it's 19. And that's stated up here. Our degrees of freedom and number are stated here. And you can see I've gone ahead and calculated our deviations. Our 15 here minus the mu of 19. And I've also gone ahead and squared them. And so now we can continue with our calculations. So we find out that the sum of squares is 30. We get that by adding up this column. We estimate our variance now, taking sum of squares divided by degrees of freedom, and we discover that 7.5 is the estimated variance. Our variance for the distribution of means, dividing that by n to take into account the sample size, is 1.5, and then we come up with our standard deviation for the distribution of means. And once again, you'll see here that this S refers to the estimated standard deviation. We can't use sigma or SD because we have to remember this is just an estimate. And so what we would write up here then is, just make sure I have my pen here, is SM equals 1.224, I'll write all the digits, 22474. Now we can continue with our steps of hypothesis testing. We find and plot the cutoff point. This time we have to use a calculator tool. We can't rely on our memory because the cutoff points are different for the t-test. And I went ahead and looked up this cutoff point, and I discovered, looking it up, that the t-score associated with alpha in a one-tailed high test using alpha 0.05, the t-alpha equals 2.13. The shaded region then is this region. That's our reject region. And as before, all of the rest of this is our fail region. Fail to reject the null. Next, we calculate and plot the sample t-score. And let me see if I did this here. There we did. I did do it. So the t-sample is just mean minus mu divided by this spread, sigma m, which is 19. That's our sample score, minus the 16 divided by this calculated sigma m, which brings us to 3.27. And if we plot that, we'll find that the 3.27 is going to be way out here somewhere. TS equals 3.27, well into the shaded region. So this would allow us to decide to reject the null hypothesis. Remember, this shaded region is always our reject region. The researcher is happy. We could go back and cross off that null hypothesis, and that would leave us with the research hypothesis, and this would be our concluding statement. Notice we do the statement exactly the same way, but in the statistic, we're now listing that it's a t-test, and instead of putting n here, we're putting degrees of freedom here. The rest of it is all the same. So what's the same about the one sample t-test when compared to the z-test? Both tests compare a sample mean to a known population mean. Both use one or two tailed tests according to the hypothesis. Both tests require parsing the problem, and both tests use the same basic formula to calculate the standardized sample score, that is the t-score. Z, look at this, sample mean minus population mean divided by spread, and T, sample mean minus population mean divided by spread. Both tests use the distribution of means based on the sample size, and both tests look up cutoff points. What's different? Well, the standard deviation is different. In the z-test, the standard deviation is provided, but in the t-test, it's not known. So we estimate the variance for the population based on the variance of the sample, and that lets us get to that standard deviation for the distribution of means. Secondly, the cutoff point. In the z-test, we use standard cutoff points based on the z distribution, but in the t-test, we look up cutoff points in the t distribution based on alpha and degrees of freedom. And finally, the standardized score. In both tests, the formula is the same as we saw on the previous slide, sample mean minus population mean divided by spread, but the symbol for spread is SM instead of sigma m because we calculated it differently.